Welcome to Brain Vision.
Hello everyone, this is a solution to problem 36 of chapter 24 of college physics. Here we're again asked to find as much of the information about this electromagnetic wave as possible, and we're given the general form for the electric field, but the amplitude of the magnetic field is missing. Nevertheless, we're told that the electric field is oscillating in the y direction, and the magnetic field is oscillating in the z direction. So we know that these two waves actually correspond to the same electromagnetic wave. Additionally, reinforcing this, we're told that the period, which appears in the argument of the periodic function, in this case a cosine, when factorizing 2 pi from the argument, we see that the period is sitting under the time argument, whereas the wavelength is sitting under the space argument of the functions. Okay, so starting with this, we can immediately read off what Emax is. So what's the amplitude of the electric field? We're told that this is 9.0 times 10 to the 5 newtons per coulomb. So we're told what this is. Now, there is a relation between the electric and the magnetic fields in an electromagnetic wave, which says that E is equal to C times B. So you can work out what Bmax is simply by dividing Emax with the speed of light. So we get Emax divided by C, where C is equal to 3.0 times 10 to the 8 meters per second. So using this value and this value, we work this out to be 3.0 times 10 to the minus 3 Tesla. Sorry, this is probably not that visible. This is a 5, so this is 10 to the 5. This is already given to you in the form of the function. So this is this value here. That's Emax. Okay, so now you know what Emax and what Bmax is. Now, again, like I said, you can just read off the period as given, as it sits under the time argument of the periodic part of the function of the wave. So reading this off, this is just 5.3 times 10 to the minus 15 seconds. This is the period. Now, we can use the period to work out what the frequency is, because the frequency is just 1 over the period. So this is 1 over 5.3 times 10 to the 15, 10 to the minus 15. And this is equal to 1.9. This is 1.9 times 10 to the 14 hertz. Okay, so now we know the period, the frequency, we know the maximum, we know the electric field amplitude and the magnetic field amplitude. Furthermore, we can work out what the wavelength is, because the wavelength, like I said, just sits under the spatial argument of the periodic part of the function once 2 pi has been factorized out. This is a really important point, because in general, you would expect something like some periodic function, let's say sine, and there would be omega times t minus plus minus k times x, where omega is 2 pi times the frequency, times the actual frequency. This is called the angular frequency, and k is equal to 2 pi over lambda. This is known as the wave number. So anyway, 2 pi has been already factorized out in the problem, so we can just directly read off what lambda is. And lambda, reading this off, is 1.6 times 10 to the minus 6 meters. Okay, so this is the wavelength. And then, just like for any wave, we can use the wavelength and the frequency, or the wavelength and the period, to find what the speed is. And the speed of the wave is given by lambda times f, or equivalently lambda over t. And so this is equal to 1.6 times 10 to the minus 6 meters times 1.9 times 10 to the 14 hertz. If you work this out, this is approximately 3.0 times 10 to the 8 meters per second, which is just the speed of light. So this is an electromagnetic wave that travels at the speed of light. It has a wavelength of 1.6 times 10 to the minus 6 meters, a frequency of 1.9 times 10 to the 14 hertz, period of 5.3 times 10 to the minus 15 seconds, magnetic field amplitude 3 times 10 to the minus 3 Tesla, and electric field amplitude 9 times 10 to the 5 meters per coulomb. Now there's two additional pieces of information that you can tell just by looking at this wave. One is that there's a relative minus sign between the spatial and the temporal modulation of the periodic function, which means that the wave is traveling in a positive x direction. And lastly, you could look up in a table what this frequency corresponds to on the electromagnetic spectrum, which would tell you what kind of wave you're looking at. Is it an X-ray? Is it a microwave, etc.? But we're not going to do that here. So this is all.